For this experiment, you're going to need 3 beakers with about 10 grams of salt in each. To clarify, the salt is just to act as an electrolyte so that your oxidation process will occur quicker. So, for each of those beakers, you will need to put 1 nail in, and then just to increase the process even faster, we're going to put all 3 beakers on a hot plate and record the temperature just to make sure the solution doesn't get too hot and boil. And for one of the beakers, you're going to put in this strip of copper metal, just like that. And for another one of the beakers, you're going to put in a strip of magnesium metal right in here. And the last beaker is just going to be the control. So you're not going to put in any other strips of metal besides your nail. So we're just heating up our solutions right now to make sure that all the salt is going to dissolve. So when the temperature hits about 80 to 85 degrees Celsius, we're going to take these off and let them cool and put the nails in to run the rest of the experiment. Now that we've dissolved all the electrolyte in solution, we can take these off now. Let those cool a little bit. And we're going to now put our 3 nails in, 1 for each of the beakers.
And 25,000.
Just take these thermometers out here. And now this beaker is going to be the control. So we are just not going to put any other metals in it and just let it sit and see the oxidation process of the metal, or the iron rather, take place. And in this beaker, we're going to put a strip of copper. Now, what you're going to see is that this will either have no effect on the iron metal, or it'll protect the iron metal from corroding. Now, with the magnesium metal, same thing. We're going to see if it can protect the iron metal from corrosion.
Here we have listed the half reactions for copper, iron, and magnesium and their corresponding reduction potentials. As we know, the more positive the number, the more likely it is to be reduced and act as an oxidizing agent. And the more negative the number, the more likely it is to be oxidized and act as a reducing agent. These reduction potentials help to explain why we see what we see in the beakers. In the copper and iron nail beaker, it's clear by the orange coloring that the nail has rusted. Looking at the reduction potentials, copper's potential is significantly greater than that of iron's. So it makes sense that copper acted as the oxidizing agent and encouraged the rate at which iron rusted. In the magnesium and iron nail beaker, there is significantly less rusting of the nail and some decomposition of the magnesium, which is in blue. Looking at the reduction potentials, iron's potential is greater than that of magnesium's. It's clear that magnesium acted as a sacrificial anode, protecting the nail from rusting through decomposition of itself. Regarding the control group, which is simply an iron nail in a saltwater solution, the nail rusted less than the nail in the copper iron beaker and more than the nail in the magnesium iron beaker. This is expected since the reduction potential of the control group's oxidizing agents is less than the reduction potential of copper and greater than the reduction potential of magnesium.
Here's a classic example of cathodic protection. If we take the nail out here, we can see that there is virtually no corrosion whatsoever, and so this nail's integrity is now preserved. Several examples of this are things such as putting an aluminum or magnesium rod inside a steel water heater, where corrosion can be very prevalent. Putting a zinc sacrificial anode on the hull of a ship to prevent this iron hull from corroding, or even putting a sacrificial anode in a structure of a building to prevent it from structural failure and damage via corrosion. So one of the main environmental concerns of using a sacrificial anode, however, is what happens to the pH surrounding the substances being corroded. For example, the solution that the magnesium and iron nail were in has turned highly basic. So what that means is that that can be very damaging to plant life and microorganisms in soil and such, and so one needs to be very careful in choosing the right metal for a sacrificial anode to prevent, when trying to protect metal via cathodic protection, that the products of the reaction are not going to be toxic to the surrounding environment.